Good evening to all of you. I will present you my bachelor thesis with a title Modeling and Attacking Strategy based on Dynamic Path Planning. So, the contents, I'll start with the goal of my thesis. After this, I will show you the Dynamic Path Planning, which is the base for the attacking strategy. And afterwards, I'll show the conclusion of my test results. So, at first, the goals. We wanted to implement a dynamic path planner which can be influenced at any time by our ELISA behaviors. So we used an adaptable heuristic for the A-star algorithm, which is the base of the path planning. And the last goal was an expandable attacking strategy that can be expanded by new plans or behaviors. So the base of our path planning approach is the Computational Geometry Algorithms Library, in short CGAL, which is an extensive collection of algorithms from the field of computational algebra. Important is that it supports both a Voronoi and a Voronoi diagram, which are the mathematical base for our path planner. So another feature is that supports dynamic inserting of Voronoi centers in an already created Voronoi diagram, which can be used to influence the path planning. Another important feature is the avoidance of degenerated edges and cells, which could be edges with zero length or areas, cells with zero area, which could interfere with the path planning. But there are some disadvantages in this library. It's partially poor documented. If you try to understand the code they have written, you can look for comments. If you find some, you can be happy. But sometimes they even switch the language in the comments, or there are no comments at all. Therefore, some algorithms, you can use them, but it's hard to understand how they even work. The base for our path planner is a Voronoi diagram, which you can see here, which it is a division of the two-dimensional space into cells by a given set S of Voronoi centers, which are marked here in red. So each Voronoi cell consists of all points in the 2D space which are closest to a given center. So, and for the path planning, we use the borders between these Voronoi cells, which can be separated into edges and vertices, which have the feature that they have a maximum distance to the neighboring Voronoi centers, which could be obstacles for path planning. So if you follow these edges, you can easily avoid any obstacle. So the path planning approach itself searches a path on the Voronoi edges with an adjusted A-star algorithm, and is divided into several steps to ensure that we can react on different situations. One of this is that we calculate a new destination if the actual destination is blocked by perhaps an opponent who is at the location we want to drive to. And it can be dynamically influenced by ELISA behaviors. So the first step of the path planning includes a verification of the corridor between the actual target, which is here, and our robot who wants to plan a path. So if the robot wants to drive from here to here, he has to check if there's a direct way and if we can skip the path planning. As you can see, then another teammate and the ball is blocking the direct path, so we have to actually use the path planner. In general, this is a screenshot of our visualization. So all obstacles are marked in blue. We have used artificial obstacles to force the path planning on the field and some of the surrounding areas. The black dashed lines are the Voronoi edges. The white dashed line is the path it has calculated, and the red dashed line is the corridor check. So the second step during the path planning is the actual use of the A-star algorithm to find the target. If the A-star finds a path to the target, we can use this and drive to the point. If the A-star algorithm doesn't find a target, we calculate a new target next to the old one, so we can at least drive in the direction. The fourth step is a special situation. It could happen that we are surrounded by obstacles, or because of bad light situations, we could see shadows as obstacles. And if the robot is surrounded by obstacles, situations could happen where we cannot move. To avoid this, we try to at least move a bit into the direction of the farthest away of the surrounding opponents, to at least make sure that that we don't see shadows, or that we can at least encounter such situations. Another feature of the path planning is the dynamic adding and removal of obstacles. As you can see here, we can block parts of the field with artificial obstacles to counter or to ensure that we stick to the rules in several situations. In this picture, you can see that the opponent here in black has a free kick, and during the free kick, we aren't allowed to get closer than 3 meters to the ball. So it's easy if we add artificial objects with a 3-meter radius around the ball, that the path planner can't even approach the ball or calculate paths which would run through this 3-meter circle. So we can easily avoid this disturbing the opponent during standard situations. The next part was modeling an attacking strategy, which consists of several ALISA behaviors and plans, and I'll show you 3 of them. The first one is used for shielding the ball. It's actually a kind of easy calculation. We have our own robot, the closest enemy to the robot, and our target point. So in the first step, we calculate the vector between our robot and the first obstacle. We turn it by 180 degrees and receive this vector, which will be a part of the alignment vector. The second part will be the vector between the own robot and the target point, and the alignment point is a weighted sum of both of them. So if we dribble to a specific point and always keep aligned to this point, we shield the ball from the enemy. So it can't see it, so the closest enemy can't see it at all. During this movement, we have to always ensure that we rotate the robot around the ball, that we can't lose it, that we can't lose the ball, because we could, if we would turn the ball around the robot, we could easily lose it. So the next behavior is checking if a path is possible. Therefore, we use the Voronoi Diagram. In this situation, the robot in ball possession should play a pass because he is blocked by 3 opponents, and the best pass would be over to this one, because he can easily score a goal because he isn't blocked and is able to shoot at the goal. But we have to use this robot as a pass receiver in order to play a possible pass. So this behavior checks if there's a possible pass point, which are marked here in blue. To calculate the pass points, we use the Voronoi vertices and move them closer to our own robot, so that the neighboring opponents couldn't actually get the ball before we can do. So if this behavior finds one of these blue points, it is successful and the next one is triggered, which is the fast pass. The first half of this behavior is the same, like checking for a pass point, but it evaluates the best pass point, and if it finds the best pass point, it sends a message to the pass receiver, here in blue, with the location where the pass will arrive, here. And after this message is sent, the actual pass is played. So the final part is the summary. I've tested the dynamic insertion and removing of obstacles in the Voronoi diagram. So I used around 10 till 1,000 obstacles during insertion and removal, and in the normal amount, like 10 till 100 obstacles, it affected the runtime of our behaviors only slightly. Our runtime shouldn't exceed 33 milliseconds, and insertion and removal of artificial obstacles takes around 1 millisecond if there are many, like 100. And if there are 10 or 20, it's way lower than 1 millisecond. The path planning is normally a very expensive operation, but if we plan a path through the whole field, it takes around 1 millisecond for 10 to 25 obstacles on the field, and the runtime gets higher if there are even more. If we would have around 100 obstacles on the field, it takes around 17 milliseconds. So in general, the runtime of our behaviors isn't affected, and we can use the path planning without losing too much time. So I've tested these behaviors I've used on our robots, and during the test they successfully avoided obstacles, and most of the time they shielded the ball almost perfectly from the nearest opponent. So. Okay.
Okay, yeah. So this looks like this is static now, so can you also take into account if the dots are moving? So then you know in advance that
this diagram is created every 33 milliseconds. So we calculate on a static one, but it's changed every 33 milliseconds, so we can react on moving obstacles.
So you don't make a proposal that you think it will go that way, so that okay.
Not so far.
Thank you.
Did you include something like hysteresis that you don't get deadlocks? For example, if the situation changes slightly because of noise on your vision, for example, that you think your opponents are slightly moving, they are not, and you might end up in a deadlock because, yeah.
Yeah, we had something like this, but we want to implement it again. So we would fuse all seen enemies of the team, so we can have more steady opponents.
Okay, but you don't keep the path, for example, and say, well, it's still valid because.
No, it's part of the A star of the hysteresis function from the A star search. So if there were already a path in one iteration before, then it tries to keep that path.
Anyone else? You gave us some numbers regarding the performance of your solution, and what is the overall overhead regarding the total software that is running the robot? Because this is only part of the job, right? You have Alisa running also on this, and you have an idea? Are you already on the limits regarding the 30 to 3 milliseconds? No, you are.
Alisa takes like, a usual Alisa step takes like 1 millisecond, and this one depends on the amount of obstacles, but its current implementation, we can assume that's again 1 millisecond.
Yeah, around.
Okay. Another short question that has something to do with what we're expecting to do tomorrow. You introduce a lot of artificial obstacles, right?
Yeah.
And do you have an internal way of determining if this is an artificial obstacle or a real obstacle?
Yeah, in our world model we have a list of all obstacles which are currently on the field, and they are you can distinguish
between them.
Yeah, on an ID we gave them.
Okay.
So we have negative numbers for artificials, positive for real ones.
Very simple solution, right?
Yeah.
Okay, thank you.
One question regarding the implementation. You mentioned that your objective is always to walk on one of those lines,
yeah.
Drive the robot on one of those lines. it's also, the question is also related to the problem that the dots are moving. And if you have one dot that comes down and the other one that goes up, the line will rotate. In terms of the implementation, do you try to drive along the line? Do you drive to the next vertex? Or?
Yeah, normally we calculate the full path, but we only use the first vertex as a goal. So it will change every 33 milliseconds, so we can easily avoid if the enemy is the opponent is moving.
Okay.